Going to cover lesson 32, simplifying expressions containing integer and zero exponents. Now, what do we mean by integers? What are the integers? Let's define this. It's all of the positive and negative whole numbers, right? Or the almost, because zero doesn't have an opposite, so you can't really use that. If you use opposites, you'd have to say it's the whole numbers and the opposites of the natural numbers, right? Yeah. So it's the number line numbers, right? So we're talking about positive and negative exponents. What do y'all remember about negative exponents? Because somebody asked in the bell work about whether that was negative exponent, right? What do you remember about negative exponents, Nick? Anything, Jeffrey?
Remember, like, we made it into a fraction and then it changed the sign of it.
Okay, that's a good memory. Hadley?
Like Jeffrey said, if it's negative, you have to change it. You can't just leave it like that, so you have to flip it.
Good. So you're remembering that having a negative exponent in your answer is bad. You can't leave it that way. That's correct. Yes?
I mean, you do it like a normal positive, but you flip it on the other side of the fraction bar.
So negative exponents flip things. So yeah, this is good. You guys are remembering some good things. Everything you said is correct, which is good. So today's lesson will be a little bit of a review, but we're going to kind of establish things. Yeah, I want you to make sure you know why. Don't just know the rule. Okay. Algebraic expressions may contain exponents that are positive, negative, or zero. Exponents can be positive, negative, or zero. Soon and very soon we're going to look at what happens when you have a fraction as an exponent. Okay? You can have rational exponents as well. All right? We can talk about and make sense of what 16 to the 1/2 power means. Or 16 to the 2/3 power. Yes. Okay. So we can talk about what those things mean. All right. The relationship between the different exponents can be understood by looking at successive powers of a positive integer greater than 1. So what I want to look at here is this table. Let's look at the powers of 2. All right. Here's the powers of 2. 2 to the first, if we go up here, 2 to the first is 2. 2 to the second is 4. 2 to the third is 8, and 2 to the fourth is 16, right? So what patterns do you see going on here? They double as they go up. What's another way you could say that?
They grow as the exponent adds 1.
The exponents are increasing by 1, and the other things are increasing by a factor of 2. If we use 3s, then we couldn't say double anymore, could we? Right. It just happens to double here because of the 2. That's why it's doubling. If this was 3 to the first equals 3, 3 to the second equals 9, 3 to the third equals 27, 3 to the fourth equals 81, then we're not doubling anymore, we're tripling it, right? We're multiplying, or we're increasing by a factor of 3. Okay? Now, so we see the pattern here. In the left column, each entry is decreasing by the exponent in the previous entry by 1. If you go down, it's increasing if you go up. And in the right column is found by halving. Is that correct? Halving or halving? Halving, whatever. The previous entry, or dividing it by 2. Right? So, if we continue the pattern, what would the next power of 2 be on the left? 2 to the 0 power. Going down. We're going to go down. 2 to the 0 equals 2 divided by 2 is 1. Right? Because to go from each of these, we're dividing by 2, right? Every time we go down, we divide by 2. And then what would be the next one here? 2 to the negative 1 power, and that's going to be 1 over 2. We're continuing the pattern, right? What are we doing here? To go from here to here, we're dividing by 2. Divide by 2. Divide by 2. Okay? All right, what would the next one be? 2 to the negative 2 is going to be 1/4, right? So 2 to the negative 2 here would give us 1/4. And then, fine, let's just do one more. 2 to the negative 3 would be 1/8. Okay? 1/16, 1/32, 1/64, etc. Now, I want to take this a little further and point out to you that this is equal to 1 over 2 to the first power. Agreed? So 2 to the negative 1 equals 1 over 2 to the positive 1. And that kind of established what some of you were saying earlier about what negative exponents do. It moves it down and becomes positive. It flips things. Right? 4 is 2 to the second. So 2 to the negative 2 is equal to 1 over 2 to the positive 2. 2 to the negative 3 equals 1 over 2 to the positive 3. Okay? Now, the most interesting progression like this is powers of 10. Our number system is powers of 10, right? Does everybody agree with that? Okay, so if we were to just take this and have a look at a number, (1,365.123), right? This is the what place? Thousandths place, which is the 10 to the third. Right, this is the hundreds place, which is 10 to the second. This is the tens place, which is 10 to the first. That's the ones place, which is 10 to the 0. Okay, this is the tenths place, which is 10 to the negative 1. This is the hundredths place, which is 10 to the negative 2. And this is the thousandths place, which is 10 to the negative 3. Right. So our number system is a base 10 number system. And powers of 10 decrease by 1 as you go down, or increase by 1 as you go up. Right? So from one digit to the next, we're increasing. All right. So here's the rule that we've just established. For every non-zero number x, x to the negative n equals 1 over x to the positive n. And it works both ways. If you have x to the negative n in the denominator of a fraction, it can flip up and become x to the positive n. I need y'all on this long Friday of this long week to dig way down deep and pull your heads up, pull your imaginations from where they are, and pay attention. Okay. Now, y'all are some tired folks today. We also learned by looking at the table that we just looked at that anytime you raise something to a power of 0, it's equal to 1. Why is it equal to 1?
Because anything divided by itself equals 1.
Okay, explain that.
X divided by x equals 1.
But why does that mean it's x to the 0?
Because you're multiplying it by 0 itself, which is practically dividing it by itself.
You know, your initial explanation was on to something, but it's not quite there. Yes.
You're not multiplying the number by anything?
Right, so, yeah, that's a little closer. Anything raised to the 0 power is 1, and I'd like to ask you guys why. What does this mean, literally?
2 to the 0.
2 to the 0 power, right? What does the exponent tell us?
There's no base.
How many times the base is being used as a factor? Okay? How many times is 2 being used as a factor? 0 times, right? So the only thing that's left, because there's no 2's here, the only thing left is this nice little invisible 1 that's always hanging out, right? So 1 times 2 to the 0 equals 1. Okay? 1 times no factors of 2. Right? Remember, there's always an invisible 1 that's hanging out to multiply. Now, what you said is very, 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 very close to being correct. You said anything divided by itself is 1. We haven't yet discussed the rule, but what do you do to exponents when you divide? Subtract. What's 1 minus 1? X to the 0 equals 1. Okay? So your explanation fell a little short, but you were onto something with your thinking there. Okay? So you've got to remember that. The fact of the matter is that any non-zero number raised to a power of 0 is equal to 1. All right? Now, here's something else that, Hadley, you mentioned this. An algebraic expression is not considered simplified if it contains negative or 0 exponents. So now we've added another definition to what it means to simplify things, right? Up to this point, what does it mean to simplify an expression? Get rid of parentheses, combine like terms, take square roots, make exponents positive or no positive, no negative exponents, no 0 exponents. All right? And this little nice note is also true here. And Nick was hitting at this with his question earlier, Nick, about whether the exponent was negative. The product property of exponents applies to negative and 0 exponents. So if we're multiplying things like x to the 6 times x to the negative 3, it's x to the third, because 6 plus, you still add the exponents whether they're negative or not. Okay. All right? So, simplify this expression. How would we simplify x to the negative 3? What's wrong with it to begin with?
It's a negative exponent.
It has a negative exponent. Negative exponents are not considered simplified. Cooper?
Let me tell you the answer.
Yeah.
1 over x to the third.
1 over x to the third is correct. All right. Now,
Absolutely incorrect.
all right. X to the negative 3 equals 1 over x to the third. Y to the negative 4 over x squared. What's wrong with this answer to begin with?
It's got a negative exponent.
Negative exponent. Is there anything wrong with x squared? No. So are we going to do anything with x squared? No.
He's cool.
X squared is home and happy.
He's chilling.
Liam?
1 over x squared times y fourth.
It's equal to 1 over x squared times y to the fourth. That's correct. Okay? The only thing that's wrong with this was we have to fix the negative exponents. That's it. Everything else is great. All right, what about this one? 1 over w to the negative 4. Hold on. Mary Helen, what do you think? W to the fourth over 1. Is the over 1 necessary? No, it's not necessary, but it's okay. It's always kind of good to keep things in fraction form. You can see what happened right there. What did we do there? We moved the negative exponent term, the factor that had a negative exponent. And the only reason we're doing this is because it's considered improper form now. Emphasis on the now. It's considered improper form to have negative exponents in your answer. Really, the reason we're doing this skill, y'all listen carefully, is because in calculus we have to do a lot of manipulations of things. And more often than not in calculus, at the beginning of a problem, we want to make our exponents negative. So in calculus, what you'll be doing more often than not to work a problem like 2 over x to the fourth is the first thing you'll do is write it as 2x to the negative fourth. So what we're doing is practicing a skill that's going to be really helpful later. You need to know how to handle negative and positive exponents and how they relate to each other. Okay? All right, next example. Evaluate this expression, a squared times b to the 0. This is the expression we're working with right here. If a equals -2 and b equals -3. First thing we're going to do is what?
Plug it in.
Yeah, so we're going to write it down and show our substitutions. That's -2 squared times -3 to the 0. What does that equal to?
4.
4 is correct.
I said 4.
Any,
I said,
listen, it doesn't matter what he said, little boys. All right. Any non-zero number raised to the power of 0 is 1. So really, we didn't even need to include this, did we? B to the 0 is 1. Yes. So -2 times -2 is 4, and we're good to go. All right? Here's another one. Evaluate the expression for b equals -3. So we've got b, 3b to the -3. I'm confused why about 6 of you guys are writing these problems down and everybody else is sitting and looking. Are y'all just that good? That's fine. Lift your heads, power through. The first thing you need to do is what?
Plug it in.
I wouldn't do that first.
Alright.
I would apply the
Combine like terms.
yeah the product rule here. -3 plus 1 is -2, and then you might want to write that as 3 over the square.
Then you can plug in.
Then you can plug in your -3.
3 squared.
That's
1 over 3.
3/9, which is 1/3. I think that's easier than making the substitution before you simplify. I could be wrong. That's confusing looking, isn't it? All right, so I think it's a good idea to do your simplification before you make your substitution. You might check yourself, one way or another, but if we did this the way it is, we move this downstairs, then we'd have 3 times -3 to the -1 over -3 to the 3rd. That's, not -1, +1. Can always tell when Hadley's tired. She's my quickest corrector. I miss you, Hadley. Get some rest. Huh? Up top we have -9, and the bottom -27, 1/3. Right? This is easier. This way is easier.
Much easier.
Okay? Do your simplification and then make your substitution. All right? The quotient property of exponents is used when dividing algebraic expressions. The property states that to divide two algebraic expressions with the same base, you subtract their exponents. So this is probably not new. Is this new to anyone? You guys have done this before, right? So it works both ways. We can subtract from the numerator or we can subtract from the denominator. So we can take this expression right here, x to the m over x to the n, right? And that's equal to, we could either subtract m from n and put it over 1, or we could subtract n from n and put it under the bottom. So you can subtract whichever direction you want to. You can subtract the numerator from the denominator, or you can subtract the denominator from the numerator. Jay, have a seat. Jay, have a seat. Okay. Then we'll go to yes. X to the 7th divided by x to the 3rd is what? X to the 4th, right? Why is it not 1 over x to the 4th?
It's not negative.
Because it's 1 over x to
if we started with x to the third over x to the seventh, what would our answer be? 1 over x to the fourth. So explain the difference between those two problems.
The larger number was on top.
There we go. The larger number was on top, smaller number was on the bottom, and then when we reversed it, we subtract. So the rule is, and what this rule told us that we could do here, is it's okay to subtract from the top or the bottom. It doesn't matter which direction you subtract. And so it makes sense to subtract the smallest one from the largest one. Right? But we're only going to do that if we're working with positive exponents. And I'm going to show you guys a little something in just a minute. Like this one. How are we going to approach this problem? Yes.
You could subtract. Well, I could do it either way.
What? Yeah, Nick.
We're gonna put x to the -7 on top of it.
Yeah, that's right. We're going to move it up there, right? And then we are going to get x to the 10th. Now, is that the same as x to the 3 minus -7?
Yes.
Yes, it is.
But not.
All right, but I want to tell you something, that when you get more and more complicated problems, it's very advantageous to you to make your exponents positive before you start doing any type of combining. Okay? Make your exponents positive and then do your multiplication or division like that. So when we have an expression like this, first thing I want you to do is make your exponents positive. Write it so that it has no negative exponents. Step number 1. All right, so what would this be after I made the exponents positive?
Y to the 6, C to the 4th over x to the 6th. Nope.
Yeah, y'all are skipping steps. I don't want you to skip steps.
Third Y to the 6th.
And then we'll have x to the 5th, y squared x. What did I do?
You flipped to the unknown.
I flipped the two negative exponents. Okay? And now I'm going to simplify everything in one step from there. Okay? And this is good practice. Do you have to do it this way? No, you don't have to do it this way. But when somebody has 20 years of algebra experience and they tell you something's a good idea, you should listen. Z to the third times z is z to the fourth. Y to the sixth divided by y to the second is y to the fourth upstairs. X to the fifth times x to the sixth is, x to the fifth times x to the first is x to the sixth.
Say.
And we're done. Yep.
It's so funny.
It is easy. All right. The intensity of sound can be measured in watts per square meter. The table below lists intensity levels for some common sounds. Okay. How many times more intense is the sound of a rocket than that of regular speech? Any ideas? Regular speech, rocket liftoff. Now notice that they're giving us answers here in ranges, right? So the noise or intensity of the sound of a rocket is somewhere between 10 to the third and 10 to the seventh watts per square meter. Okay, that's a pretty big range, right? And regular speech, it depends on whether it's Mary Helen talking or Nick House talking, right? So you've got 10 to the -9 to 10 to the -6. Yep. All right, so we need to compare these numbers, and we need to compare these numbers. How many times greater is that? 10 to the 12th, right? All right, 2. How many times greater is this? 10 to the 13th times greater. Okay. And that is the answer.
That ain't hard.
It's really not. Once you wade through the notations and see exactly what they're asking you to do, it's not that difficult. All right, your homework is page 201. Same as last time.
Okay.
All right.